Algebra 2 Cram, New York State Algebra 2 Regents, Common Core, solve logarithmic equations. Question 5, quotient property of logarithms. The odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. If I could stick every single math student with a syringe containing a healthy dose of eye-opening awareness of their inner mathematical genius, I probably would. So inbox me at emedicine@gmail.com to purchase and order the complete Algebra 2 cram session beyond the solving logarithmic equation series to get your healthy dose of Algebra 2. You have lots of friends, classmates, and their colleagues who can really benefit from this cram session as well. So tell them to inbox me at memedicine@gmail.com so that they too can order and purchase the complete cram session. You'll be glad you spread the word because they'll make great study buddies. Let's delve into the concept. Question 5, logarithmic equation. Solve for x. The log base 4 of x squared plus 3x minus the log base 4 of x plus 5 is equivalent to 1. Definitely press pause if you need to, and I'll give you a moment to think. All right, so hopefully by now you are able to press pause and arrive at an answer. And if you didn't, that's completely fine. The first thing that we're going to do is basically use the quotient property of logarithms to combine the two logarithm terms into one. And the quotient property of logarithms says that the difference of two logarithms with the same base, of course, is equal to the logarithm of their quotient. And the amount being subtracted is always going to be placed in the denominator, as shown here. Okay, so here we have our original logarithmic equation, and then we apply the quotient rule or quotient property of logarithms to condense the two separate terms into one on the left-hand side. Now, to undo the logarithm on the left-hand side, we're going to raise base 4, this is the base specified in the logarithm, to the terms on both sides of the equation, because if we raise the base 4 on the left-hand side, we also have to do that on the right-hand side. So 4 raised to the log base 4 of x squared plus 3x divided by x plus 5 is equivalent to 4 raised to the first power. Okay? And basically, raising a base of interest to its logarithm just basically undoes the logarithm and the exponential equation because they're inverse functions of each other. Okay? And all right, so let's represent this. And now that the equation is rewritten in exponential form, with our exponent on the right-hand side, we can more easily solve for x. We're going to evaluate the term on the right-hand side, and we get that x squared plus 3x divided by x plus 5 is equivalent to 4. Now what we can do is cross multiply, and we're going to just transform the 4 on the right-hand side into a fraction to better illustrate this cross multiplication. So we're going to end up with x squared plus 3x is equivalent to 4 times x plus 5, okay? Now we can distribute the 4 on the left-hand side, and we get that 4x plus 20 equals x squared plus 3x, all right? All right, so now obviously what we have on our hands is a second degree polynomial, and what we're going to do is write everything in standard form. What I went ahead and did was combine the x terms by subtracting 3x from both sides of the equation. okay? And then I brought it over here to the right-hand side in an attempt to reach standard form. Remember that standard form for a second degree polynomial basically has the format ax squared plus bx plus c, where the coefficients in front of the x and c terms and even the x squared can be negative. So basically I brought the 20 over to the right-hand side by subtracting 20 on both sides. Now I'm just going to reverse this entire equation so you can better see and visualize the second degree polynomial in standard form. Okay. All right, this is a really cool problem because it's actually combining logarithms, exponential equations, and polynomials, which people sometimes confuse for exponential equations. Notice a second degree polynomial has the reverse format of an exponential equation, where the base would be a constant and the exponent would be a variable. It's actually the reverse for a second degree polynomial. So this is a really cool problem. Now, what we're going to do, because we have our second degree polynomial in standard form, we're going to solve for the roots. That is, we're going to solve for the x terms, and it's a second degree polynomial. I can't stress this enough. That means there's going to be two possible values of x, okay? So we basically FOIL, and we come up with, we open up our two sets of parentheses, we place x, and we basically look at the constant, and we try to figure out which two numbers do we multiply to get negative 20 and add to get negative 1, and basically that's going to be negative 5 and 4. All right, now we're going to separate our roots and solve for x. So this can be re-expressed as x minus 5 is equivalent to 0, or x plus 4 is equivalent to 0. And you would know how to do this and understand how we got from here to there if you watch some of my basic series videos on evaluating polynomials. That's why you should definitely purchase the entire Algebra 2 Cram session. Yeah, so after we evaluate each possible 0, we get that x can be equivalent to 5 when we add 5 on both sides, or x can be equivalent to 4 when we subtract 4 from both sides of the equal sign, okay? And because we have these two roots or two x values, we should definitely go back and check, okay? The first thing that we're going to do is plug 5 into the original equation to see if in fact x is equivalent to 5, all right? So when we plug 5 in for the value of x, we get the log base 4 of 5 squared, or 25, plus 3 times 5, which is 15, so this should be 40 over here, minus the log base 4 of 5 plus 5, and when you evaluate this, it's going to be a 10, is equivalent to 1. All right, and again, we're going to apply the quotient rule of logarithms, where we combine the two separate logarithmic terms into one by taking the log base 4 of the quotient of 40 divided by 10. And we get that the log base 4 of 40 divided by 10 is equivalent to 1. When we evaluate the quotient, we get the log base 4 of 4, and the log base 4 of 4 is in fact equivalent to 1, okay? And why is that? Well, the logarithm, basically the logarithm tries to establish what exponent do you have to raise the base to in order to get this power. The answer written along the same lines, or the numeral written along the same lines as the log, not the subscript, is basically the power, the result. It's like a backwards exponential equation. We're trying to figure out how we got from here to there using what exponent, and raising 4 to the first power will in fact yield a power. No, raising 4 to the first, or to 1, because saying to the first power is actually a misnomer, although that's a common way to express this phenomenon in mathematics. It's actually wrong. The power is the result. This is the first power result of raising base 4 to 1. Yes, so that checks. That means 5 is in fact a value for x. Now we're going to do the same thing using -4, because that was the other result that we got for x. So the log base 4 of -4 squared, which is going to yield 16, plus 3 times -4, which yields 12, so that means you get 4 in here, minus log base 4 of -4 plus 5, and that's going to simplify to 1, is equivalent to 1. Let's see this. Well, we just found out that the log base 4 of 4 is equivalent to 1, minus the log base 4 of 1. Well, anytime you get a power result of 1 and the base is some other numeral, that means you raise that base to the 0 power. So the answer here is 0, and obviously the answer here is 1. So is 1 minus 0 equivalent to 1? Well, yeah, it pretty much is, okay? So both answers check and both x values are valid. The answer is positive 5 or -4. Thanks for tuning in. Good luck studying.